Hello everyone. I wanted to make a quick video going over the application questions for today. I can't do this every day, but with the exam coming up, I think it's important that you have the correct answer worked out for you. As I know, working with these Hardy-Weinberg equations and calculating these frequencies is complicated. Okay, so let's look at this first question that you were asked. Consider a population of 1,000 skunks. There is a mutation in the gene B that makes it so that it can't spray N-butyl mercaptan. That's the stinky stuff. From the genotypes listed below, calculate the genotypes and allele frequencies of big B and little b. So first thing we want to do is calculate the genotype frequencies. And we know, and the problem told you this, so I'm going to write them down here, that the three genotypes present are big B, big B, little b, and little b, little b. So homozygous dominant, heterozygous, homozygous recessive. And the problem tells us that we have 400 skunks that are big B, and we have 500 skunks that are heterozygous, big B, little b, and 100 skunks that are homozygous recessive, little b, little b. So in order to calculate the frequency of big B, we'd divide 400 by the total number of skunks, 1,000. And that is equal to 0.4, which is the same as 40%, but it's best to keep it in the decimal form. Same logic here with the heterozygotes, big B, little b. There are 500 skunks that are the heterozygote. We divide that by the total number of skunks, 1,000, and that is equal to 0.5. And we know that there are 100 skunks that are homozygous recessive, little b, little b. We want to know their frequencies. We take 100, we divide that by 1,000, and that is equal to 0.1. And as I've said, make sure you add these up because I always make simple little math errors, and so I want to make sure that this adds up to 1. So 0.4 plus 0.5 plus 0.1 is equal to 1.0. So these are our genotype frequencies. Now let's calculate our allele frequencies. And we have two alleles in this population, big B and little b. So first what we want to do is add up all the big B alleles in this population. And we know that there are 400 skunks that have the genotype of big B. So that means every skunk has two big B alleles. So that's going to be 400 times 2. Again, that's because there are 400 skunks. Each of them have two big B alleles. So 400 times 2. Are there any other big B alleles in this population? And yes, the heterozygotes, they each have one big B allele. They also have one little b allele, but we're not worried about that right now. We're only looking at the big B alleles. So we'll go plus 500. And this equals 1,300. Now to get the frequency, we need to divide 1,300, and remember that's the total number of B alleles in this population, 1,300, by the total alleles in this population. There are 1,000 skunks in the population, as the problem tells us. Each of those skunks have two alleles, either big B or little b. So if there are 1,000 skunks, each have two alleles, we have a total of 2,000 alleles. We take 1,300 and we divide it by 2,000 and we get 0.65. This is the frequency of big B alleles in this population. Now let's calculate the little b alleles in this population. We know that the heterozygotes here, they each have one B allele, just like they had one big B allele, but now we're looking at little b alleles. So each one of these individuals, these 500 individuals, have one little b allele. So we put 500 here. Then we have to add in the other little b alleles in the population, and we see that the homozygous recessive skunks in this population, they each have two little b alleles. Okay, so each one of these 100 have two little b alleles. So we have to multiply 100 by 2. 100 times 2 is 200. 200 plus 500 is 700. We have a total of 700 little b alleles in this population. And we still divide it by 2,000 because there's still 2,000 total alleles in this population. And when you do that, you get 0.35. Okay, we're going to need to remember these numbers so we can apply them to the next question. In the next question, we're going to look at the next generation of skunks and see if the B allele is in Hardy-Weinberg equilibrium or if it is out of Hardy-Weinberg equilibrium. Okay, so now we're going to look at the next generation of skunks. And ultimately, what we want to know, we want to know if the big B and little b alleles from the previous generation and this new generation, if they're in equilibrium. And in order to do that, we need to figure out the allele frequency and genotype frequencies of this next generation. And all that we've been told so far is that the frequency of skunks that cannot spray that stinky stuff, that is the little b alleles, is equal to 0.36. And that should be enough to figure out the rest of this problem. But let's break this down. Let's remember a few things. And I'm going to write them over here. P is equal to the frequency of the dominant allele, in this case, big B. Q is equal to the frequency of the recessive allele, that is the little b allele. P square is equal to the frequency of the homozygous dominant allele. In this case, it's going to be big B, big B. 2PQ is equal to the heterozygotes in the population. That is the frequency of the heterozygotes, big B, little b. And then Q square is equal to the frequency of the homozygous recessive individuals in the population. In this case, little b, little b. All right, so we're going to solve this first equation first to determine the allele frequencies of big B and little b. So P plus Q is equal to 1. We can calculate Q because we know that little b is equal to 0.36. If we take the square root of each side here, we'll end up with the frequency of B is equal to 0.6. And remember, in our equation, B is what Q is. So we know that P plus 0.6, which we just calculated up here for the frequency of the little b allele, is equal to 1. To figure out what P is, all we have to do is subtract 0.6 from each side. So P is going to be equal to 1 minus 0.6, or 0.4. So to summarize part A here, we know that P is equal to 0.4. And we know that Q is equal to 0.6. And again, remember, P is equal to the frequency of B, and Q is equal to the frequency of little b. So we've answered this first part here. Now we need to answer the second part, the genotype frequency. So we need to do this bottom part here. What is P squared, what is 2PQ, and what is Q squared? I'm going to erase this here, and let's write this second equation out. P squared plus 2PQ plus Q squared is equal to 1. So I should have kept the values of P and Q up here, but I'm just going to write them over here so we don't forget what they are. Remember, P was 0.4 and Q is 0.6. So now we just plug these in. So P squared is 0.4 times 0.4, or squared. And 2PQ is equal to 2 times 0.4 times 0.6 plus Q squared. And Q, remember, is 0.6, so that's going to be 0.6 squared. And this should all add up to 1. So 0.4 squared, that's 0.4 times 0.4, is equal to 0.16 plus 2 times 0.4 times 0.6, which is equal to 0.48, plus 0.6 squared, which is 0.36. And we should check our math, make sure it adds up to 1 to make sure we didn't make a silly mistake. So 0.16 plus 0.48 plus 0.36 needs to add up to 1, and it does. So we know our frequency of big B is 0.16. So let's write that over here. And we know our frequency of big B little b is 0.48. And we know our frequency of little b is 0.36. I'm going to keep this side over here because we're going to look at these numbers for part C. Okay, so for part C, what they're asking us is using the genotype and allele frequencies from both populations, that is from this generation here and the previous generation on the previous whiteboard, are they in Hardy-Weinberg equilibrium? So remember, this is generation 2 here, and let's remind ourselves what generation 1 was. The frequency of big B and the frequency of little b were 0.65, and little b, remember, was 0.35. The genotype frequencies of big B was 0.4. The frequency of big B, little b, the heterozygotes in generation 1, was 0.5. And the generation of little b in generation 1 was 0.1. And we can compare these now, and we can say, by looking just at these numbers here, that there appears to be quite a big change between generation 1 and generation 2. That the allele frequencies have switched. In fact, they've kind of flip-flopped. There are now more little b's than big B's. And the genotype frequencies have also switched. Big B is now 0.16 instead of 0.4. Little b has jumped from 0.1 to 0.36. So something between generation 1 and generation 2 seems to have favored the little b allele. What that is, we don't know. But what we would conclude, though, is that these populations here between generation and generation 2 are not in Hardy-Weinberg equilibrium. That is, when you look at genes B, we would say that gene B, little b, has undergone some kind of evolutionary event. Now remember, we're only talking about gene B. There are many other genes in a skunk, right? And maybe these other genes are still in Hardy-Weinberg equilibrium. All we can say is that gene B is no longer in Hardy-Weinberg equilibrium. Now why would that be? Well, the question D asks, why are they not in Hardy-Weinberg equilibrium? So the reason they're not in Hardy-Weinberg equilibrium could be one of 5 different reasons. That is, one of the assumptions of the Hardy-Weinberg principle are no longer upheld. So for instance, maybe mutations have occurred. Maybe the big B allele, for whatever reason, has gained more mutations in it to make more little b's in that population. Maybe genetic drift happened. For whatever reason, a part of this population was lost between generation 1 and generation 2, and out of chance, more individuals with the big B allele were lost. Gene flow could have happened. Individuals could have entered this population, bringing in more little b alleles. Individuals from this population, from generation 1, that had the big B allele could have left the population. Somehow or another, individuals left or entered the population that changed the allele frequencies. Natural selection could have happened. Maybe there's some adaptive advantage to organisms with the little b allele. Maybe there's a heterozygous advantage situation. Maybe not having a stinky smell in this population was an advantage. Maybe they no longer needed that as a defense mechanism. We don't know. But it's possible that natural selection favored the adaptation of not having the stinky smell. Finally, maybe the matings between these skunks were not random. For some reason, if this were the case, more individuals of the little b allele were selected for mating. Maybe in this population, it was in a city, and they were forcing non-stinky emitting skunks to mate with other non-stinky emitting skunks to make more of those in the population so they didn't spray our dogs and stuff like that. Not saying we should do that. I'm just saying that could be an explanation why in the second generation we have more little b alleles. So any one of these could be the case, and based on the problem I gave you, we don't know. So if you get a problem like this on an exam, you would come up with one or more of these depending on how many I ask. And you would just make an explanation as how one or more of these could explain how the populations fell out of Hardy-Weinberg equilibrium. Now, I could ask you a question that gave you a little bit more information. I could say an epidemic happened in this population and it wiped out a large portion of this population. Then you would want to focus on genetic drift. Or I might say a neighboring town brought by an additional 500 skunks into our population from generation 1. And then you'd want to focus on gene flow. So I could lead you into one of these answers as the correct answer. So just make sure you pay attention to the question and answer what the question is asking. I hope this helps explain this concept a little bit better. We didn't have a lot of time to close it properly in class, but I wanted you to have the answer before Wednesday because I know you are studying for the exam, and there's no reason to wait to have the correct answer. All right, the homework for this week will include a problem like this, so you'll have more time to practice this on your own. If you have any questions at all, please let me know. I'll be happy to answer any questions you have. If not, I will see you in class on Wednesday. Have a good one. Bye.